welcome to another episode of Old Guy Physics. And we just finished a video called an Atwood device. And I wanted to go and show two other examples of where the Atwood calculations apply. And let's see if that doesn't make some sense, because those kinds of problems will probably show up on the test coming up next Tuesday. So let's take a look at a couple of these. First of all, let's draw a picture of a tabletop, and the pulley this time is going to be over here, and the block has a cable attached again, and there's a weight hanging off the table like that. And let's say that this is a 2 kilogram weight and this is a 4 kilogram weight, and let's have a coefficient of friction along the table equal to 0.30. Okay? So again, we have to establish some guidelines here for these Atwoods. First of all, there is a force of 20 newtons acting in the down direction, and the tension, which we're going to label T, is pulling up on that. There is some friction here, but we need to solve for the forces that are acting on this block so we can see whether this force that's hanging off the table is sufficiently large to make the 4 kilogram block slide to the left. So right away, we're going to label this, and this is a 40 newton box, so the normal force is also 40 newtons, and we're looking for the force of friction here, and the tension is on the string. That would be our applied force, is the tension on the string. So what we're looking for here is, what is the force of friction? And so we remember that the force of friction is equal to the coefficient of friction times the normal force. So 0.30 times 40 should give us a value of 12 newtons. And so we have a frictional force of 12 newtons acting to the right. Now, we've got to remember that the forces in this thing have to be according to the direction of the motion. And the only forces acting in the direction of the motion are going to be the tension over here pulling the block to the left, and the frictional force, which is trying to prevent the block from moving to the left. Okay? So we've got all of our forces drawn in the equation, or in the problem. And so let's go back and refresh to look at our easy way for solving Atwood devices. It's the difference of the forces divided by the sum of the masses is going to give us the acceleration. So now, you've got a 20 newton force here, and you've got a 12 newton force there, so it's the difference of 20 minus 12 on the top, and the difference of the mass, or the sum of the masses, excuse me, is 4 and 2 is 6. So I'm going to have 6 kilograms down here in the bottom, which is the sum of the masses. Now, 12 subtracted from 20 is going to be 8, divided by 6 is going to give us an acceleration of 1.33, repeating, meters per second squared. Now, to solve for the tension, you'll remember that I think that it'll be easier if we use this one, where it said capital M1G minus T equals capital MA. So if I add T to both sides, like that, then this one cancels. And then I'm going to subtract capital MA and subtract capital MA from both sides of the equation. Now that cancels, leaving T on this side, and capital M1G minus capital M1A will be equal to the tension. So M1G is just 20 newtons. Now that's going to be 2 times 1.33, repeating, So that's going to be minus 2.67, so if we round it off. And so we're going to subtract 2.67 from 20 to get the tension. And that comes out to 17.33. Is that correct? I think so. Yes. And so the tension on the cable, either the tension here or the tension here, will be 17.33 newtons. Now think about what we just said in a previous problem. 17.33 is less than 20, which is why this is allowed to go towards the floor. The 17.33 here is a stronger force than the 12, so the block's going to slide to the left at the same acceleration as this one travels towards the floor. Does that make sense? Okay, I've got another problem, but let's make it into a second video. Please hang on and we'll be right back.